6 continents adrift in a vast ocean. This is the image of our world, etched into the collective human consciousness. But it is a fleeting snapshot in the deep time of the planet. For over 4.6 billion years, Earth has been a world of profound transformation. There have been epochs when ice sheets, miles thick, entombed nearly the entire surface. In others, the poles were free of ice, and sweltering jungles thrived under a relentless sun. The very ground beneath our feet has never been still. Continents have drifted, collided, and merged in a slow tectonic ballet. This planetary dance has, on occasion, resulted in the birth of supercontinents, colossal land masses uniting nearly all the world's dry land. 335 million years ago, one such giant dominated the globe, a single, sprawling continent set in a single, world-spanning ocean. It was named Pangaea, a title from ancient Greek, meaning all earth. But this was an alien world. The climate was extreme, far warmer and drier than our own. The immense interior of Pangaea was a harsh desert, hostile to most forms of life. This new reality triggered a catastrophic mass extinction, one of the most severe in the planet's history. Survival demanded radical adaptation. Amphibians, desperate to retain precious moisture, evolved in startling ways. Some grew to monstrous sizes, while others shrank. Many delved arid air. The flora underwent its own revolution. The age of lush ferns and lycopods withered, giving way to more resilient drow. Then, around 200 million years ago, the great supercontinent began to die. Driven by the immense heat churning in the planet's core, the tectonic plates began to shift and rupture. Pangaea, the all-Earth, began to fracture, its fragments slowly drifting apart over millennia to become the continents we recognize today. The world we inhabit was forged in this great sundering, yet the forces that tore that ancient landmass asunder are still at work. The map of our planet is not a static portrait, but a single frame in an epic of creation and dissolution. The continents continue their silent, imperceptible journey, a constant reminder that nothing, not even the shape of the world itself, is permanent. The surface of our world is a restless thing. Over the immense, almost unimaginable expanse of geologic time, the continents have engaged in a slow, silent dance, a cycle of assembly and dispersal. This is the planet's deepest rhythm, a story written in stone and etched across the ocean floor. It is a chronicle of rock formation, of the birth and death of landforms, the rise and fall of seas, the coming and going of ice, and the ceaseless parade of life and extinction. A supercontinent is more than just a collection of land masses. It is a planetary force, a structure so vast it fundamentally alters the circulation of heat from the Earth's core and dictates the flow of global air currents. It need not unite every continental block, but its sheer scale reshapes the world. The most famous of these titans was Pangaea. Its assembly began some 335 million years ago, a colossal merger of older continents during the Paleozoic era. The evidence for its existence is overwhelming, woven into the fabric of our planet. In the geological strata, the fossil records, the paleoclimatic data, and the precise measurements of our modern age. They all tell the same tale. The continents we know today were once locked together, neighbors in a single, gigantic, planetary structure. Where these ancient lands collided, mountains were born. The Urals and the Appalachians are the deep roots of these primordial ranges, the weathered scars of Pangaea's violent creation. They are immeasurably older than the planet's younger, sharper mountains, the Alps, the Cordillera, the Andes, or the Himalayas. Worn down by hundreds of millions of years of erosion, they stand today as quiet monuments to a time of unimaginable upheaval. Most of this gargantuan landmass was clustered in the southern hemisphere, surrounded by a single world-spanning ocean known as Panthalassa. Life in this era was utterly alien. The climate was warmer, the flora and fauna a lost world of evolutionary experiments. Then, between 150 and 220 million years ago, the great sundering began. Pangaea fractured. From its northern half, Laurasia, the land masses of Eurasia and North America, would eventually drift apart. From its southern half, Gondwana, came the continents of Africa, South America, India, Australia, and the frozen expanse of Antarctica. But Pangaea was not the first. Before it, there was Rodinia, another vast assembly that broke apart roughly 750 million years ago. The cycle is relentless. Projections suggest that in 250 million years, the continents will converge once more. Africa, the Americas, and Eurasia are on a collision course to form a new supercontinent, tentatively named Pangaea Ultima. As early as the 70 of Newton began to gaze at the world's maps and wonder at the curious fit of the coastlines, seeking to explain the origins of our planet's topography. They were glimpsing the first clues of a truth far grander than they could have imagined. The world map we hold in our minds is but a single frame in a film that runs for billions of years. We live in a fleeting moment of dispersal on the scattered fragments of a world that was, and a premonition of a world that is yet to be. For centuries, an impossible truth lay buried in stone. The remains of marine creatures, discovered high in mountain ranges far from any shore, whispered of a world in constant flux. They were evidence that the very contours of the seas and lands had shifted throughout the deep history of the earth. Yet, by the dawn of the 20th century, this ancient wisdom had been forgotten, replaced by a rigid certainty. The consensus among geographers was that the planet's face was fixed. The continents and oceans, they believed, had remained unchanged since antiquity. The planet's great mountains and valleys were seen merely as wrinkles on the skin of a cooling world, the result of uneven contraction, or perhaps the simple accumulation of sediment over eons. The Earth was a static stage. This dogma would be challenged not by a geologist, but by an outsider, a German meteorologist and astronomer named Alfred Wegener. He would champion two of the most disruptive ideas in the history of science: that the continents themselves were adrift, and that once In the distant past, they had all been joined together in a single, colossal supercontinent he would name Pangaea. The revolution began not in a laboratory, but with a simple gift. In the winter of 1910, Wegener's roommate received a New World Atlas for Christmas. As Wegener studied its pages, his gaze was arrested by the coastlines bordering the Atlantic. He saw what countless others had seen, but he perceived it with new eyes. The great bulge of Brazil seemed to fit perfectly into the deep curve of West Africa. It was a tantalizing, impossible similarity, a ghost of a connection. The idea took root. In the autumn of 1911, Wegener stumbled upon paleontological studies he had never known existed. They spoke of identical fossil species found on the separate shores of Brazil and Africa, creatures and plants that could never have crossed the vastness of an ocean. The map's suggestion was now supported by the silent testimony of the dead. For Wegener, this was the final galvanizing proof. Inspired, the 31-year-old scientist dared to present his radical concept. On the 6th of January, 1912, before the German Geological Association in Frankfurt, he declared that the continents had not always been where we find them. They were restless wanderers on the planet's surface. The reaction was not curiosity, but scorn. The assembled authorities met his hypothesis with open hostility. To the geologists committed to a fixed Earth, the very notion that entire continents could move was absurd, a scientific heresy. They dismissed Wegener as an inexperienced amateur, a meteorologist meddling in a field he did not understand, ignorant of the established paradigms. His theory, while elegantly explaining so many of the Earth's mysteries, had a fatal flaw. Wegener could not answer the most fundamental question of all: what titanic force, what unimaginable engine, could propel entire continents across the face of the globe? This single, unanswered question was enough to condemn his idea. And so, a revolutionary truth was cast out, rejected by a world not yet ready to see itself as it truly was. It was a vision of a dynamic, breathing planet, dismissed as fantasy, left to wait in the wilderness of scientific thought for the evidence that would prove the world itself was in motion, and that sometimes the most profound truths are found not in the answers we possess, but in the courage to question the very ground beneath our feet. For generations, the Earth was seen as a world of permanence. The continents were thought to be the primordial remains of the planet's oldest crust, relics forged in the melting bowels of a young world. These great land masses were believed to be immovably anchored, their positions fixed for all time. The Earth's skin, its crust, was thought capable only of vertical motion, sinking to form the vast ocean beds, or rising to build the continents and thrust mountains toward the sky. Any horizontal movement was dismissed as trivial, an insignificant tremor on an otherwise static stage. The engine of all change was assumed to be simple, the slow, inexorable cooling of the planet's fiery heart. Within the respectable geological circles on both sides of the Atlantic, This was settled science. Any alternative was considered incoherent, a fantasy unsupported by fact, and mechanically implausible. For a long time, the very notion of a mobile Earth was deemed so negligible it barely registered in the sphere of serious debate. But one man, Alfred Wegener, was utterly convinced by a different vision, a new perspective on the entire geological history of the planet. He refused to abandon the work he had begun. His lonely pursuit was fueled by a profound perseverance, and aided, ironically, by the fact that his critics had never bothered to seriously analyze the arguments he was assembling. And so, Wegener began a methodical, comprehensive search for data that could illuminate the problem. He hunted for clues across disciplines, piecing together a puzzle of a world in motion. The result of this monumental effort was published in 1915. The book, The Origin of Continents and Oceans. It contained not only the radical new concept itself, but a solid and versatile justification for it. With its publication, the innovative hypothesis could no longer be so easily ignored. Despite the immense pressure of the prevailing fixist paradigm, a few serious researchers, their curiosity ignited, began to make themselves known. The most critical contribution came from the British geologist Arthur Holmes. He proposed the missing mechanism, the driving force powerful enough to move continents. He envisioned immense convective flows of matter churning in the depths of the earth. Hot masses, he argued, would slowly rise from the planet's interior, while cooler, denser rock would gradually sink back into the mantle, creating currents that could carry the continents. Wegener's most important disciple at this time was the South African Alexandre du Toit, one of the world's greatest field geologists. Embracing the concept of continental drift and drawing upon his own vast experience, du Toit began to advocate for a more nuanced history. He argued that in the distant past there was not one single supercontinent, Pangaea, but two, Laurasia to the north and Gondwanaland to the south, separated by the waters of an ancient ocean named Tethys. The continents had not been the only things to shift. So too had the very foundations of human understanding, revealing a planet far more dynamic and a history far more restless than had ever been imagined. The seeds of a revolution lay dormant in the theories of the Austrian geologist Edward Suess. He spoke of a lost world, conjuring names for an ancient ocean, Tethys, and a vast southern continent, Gondwana, a primeval landmass that once bound together Africa, Madagascar, and the peninsula of India. In time, this vision of Gondwana would expand, its conceptual shores stretching to embrace South America, Australia, and the frozen expanse of Antarctica. To the north, a second supercontinent was proposed, Laurasia, the hypothetical union of North America and Eurasia. The world's great land masses were being reassembled, piece by painstaking piece. But the ultimate key to this planetary puzzle was not found on land. It lay hidden, deep beneath the waves. It was realized that immense mid-ocean ridges, chains of submerged mountains, snaked across the entire globe. Then In 1953, the American physicists Maurice Ewing and Bruce Heeson made a startling discovery. These ridges were fractured, split by deep trenches that plunged into the very crust of the earth. A few years later, another American scientist, Harry Hess, offered a breathtaking explanation. This global ridge system he proposed was a wound that never healed, a zone where new oceanic crust was perpetually being born. Hot magma, the planet's lifeblood, surges through these fissures to the surface, relentlessly pushing aside the seafloor on either side. Here, at last, was the engine of creation, the immense, unseen force driving the continents themselves. By the mid-1960s, the once heretical hypothesis of Alfred Wegener was finally embraced, becoming the bedrock of modern geography. The scientific community had come to appreciate the sheer weight of evidence he had gathered decades before. The geological clues were undeniable. The uncanny fit between the Atlantic coasts of South America and Africa, the way ancient mountain ranges on one continent aligned perfectly with those on another, as if they were lines of text from a single torn page. The very story of the rocks, told in their layers and composition, was identical across the oceanic divide. And the fossils told the same tale, explaining the inexplicable, how the same species of plants and animals from the Paleozoic and Mesozoic eras could be found on continents now separated by thousands of miles of open water. Yet even as this grand picture took shape, a glance at the world map revealed another, more subtle possibility. The Iberian Peninsula, home to modern Spain and Portugal, corresponds with remarkable precision to the shape and scale of the Gulf of Mexico. The peninsula of Florida, which guards that gulf, seems to find its inverse reflection in Europe's Bay of Biscay. This is not mere cartographic coincidence. The proof is etched into the earth itself. Deposits of rare heavy metals, almanite, rutile, zircon, and monazite, are mined off the coasts of Florida, within the Gulf, and again across the vast Atlantic, off the shores of Iberia. The map of our world, it seems, is not a static portrait, but a momentary frame in an epic of unimaginable scale. It is a chronicle of immense forces and deep time, a story of separation and collision, written in stone and water, forever waiting for us to learn its language. A chasm was opening between the sciences. The established narrative, a story of a fixed and static Earth, championed by geologists, could no longer reconcile the strange and compelling tales told by the planet's flora and fauna. The living world and the ghosts of worlds past whispered of a different history, a time of intimate proximity between lands now separated by vast oceans. Consider the enigma of the European eel. Each year, it undertakes a seemingly impossible pilgrimage, abandoning the rivers of a continent to journey 6,000 kilometers across the Atlantic. Its destination, the Sargasso Sea, a strange, placid vortex of water just north of the Florida Peninsula. Here it spawns, and here it dies. This extraordinary act may be nothing less than an atavism, a ghostly echo of a forgotten geography. 130 million years ago, when the continents were huddled close, this same journey was but a short swim. The eels that settled in the nascent rivers of Europe carried this ancestral map within them, a map whose scale has been stretched by the slow, inexorable drift of the world itself. This ancient cartography points to a startling conclusion. For the eels to colonize the British Isles, the Bay of Biscay must have once neighbored not the northern shores of America, but its southern coast. The mystery deepens with the horseshoe crab, a living fossil that has scuttled through Earth's seas for hundreds of millions of years. Today, these creatures are found only in the warm waters of the Sargasso Sea and the Gulf of Mexico, and yet their fossilized remains are unearthed thousands of miles away in the cold clay of the British Isles. Once again, the evidence is inscribed in stone. Northern Europe was once tethered to the Gulf of Mexico. The author of this radical new hypothesis, the meteorologist Alfred Wegener, sought proof not just in life, but in climate itself. He traced the scars left by ancient glaciers and mapped the boundaries of fossilized climate zones. This data, too, confirmed his vision of a world in motion, allowing him to reconstruct the positions of continents by the weather they once endured. But for the geological community, a tapestry of compelling clues was not enough. All these arguments, all this evidence, were deemed insufficient. They pointed to a radical effect but could not explain the cause. A colossal question remained unanswered. What titanic force could possibly move a continent? Then, in 1930, on the desolate ice sheets of Greenland, the theory's architect was lost to the world. In the silence that followed, the hypothesis of continental drift began to founder. Opponents, emboldened, attacked its weakest point, the missing mechanism. The criticism was relentless, and with its champion gone, unanswerable. The idea was pushed to the fringes, dismissed as fantasy. Mobilism, as it was known, was purged from the realm of official science, erased from the curricula of universities. It became a scientific heresy. But an idea, once spoken, rarely vanishes completely. It merely lies dormant, waiting. In the aftermath of the Second World War, new technologies began to probe the planet in ways previously unimaginable. The active search for clues in the Earth's magnetic field and the intensive sounding of the ocean floor with echolocation would soon uncover the very engine Wegener could only guess at. The truth had not disappeared. It had simply been waiting beneath the waves. For the story of our world is not written in the doctrines of men, but in the stone and the sea, waiting for the tools and the minds bold enough to read it. A body of evidence once pointed to an impossible geography, a time when the Iberian Peninsula rested in the warm embrace of the Gulf of Mexico. This was not a flaw in the data, but a profound clue, a whisper of a world in motion. To explain it, old theories had to be reborn, and a new understanding of our planet forged. The truth, when it was finally unveiled, was far more profound than drifting continents. The entire crust of the Earth, it turned out, was fractured into immense, separate sections, colossal rafts of rock we now call plates. It is not the land masses themselves that wander, but these vast plates, carrying the continents as passengers upon their backs. The driving force is a hidden engine of unimaginable power. Convective heat flows from the Earth's mantle. Gigantic slow-motion circulations of superheated rock rise, spread, and sink, pulling and pushing the rigid crust above in a silent, ceaseless dance. By the early 1960s, this new evidence breathed life back into a once dismissed hypothesis, giving it a new name: plate tectonics. Today, we see the Earth's surface as a dynamic mosaic composed of 7 great plates and a host of smaller ones, all locked in a perpetual grinding ballet. They collide, they pull apart, they scrape along each other's edges. Where an oceanic plate meets another or a continent, one is forced to surrender. A subduction zone is formed. The edge of the descending plate plunges into the depths, diving beneath its neighbor to be consumed. At a depth of 100 kilometers or 60 miles, it melts completely, reclaimed by the mantle in temperatures that exceed 1,500 degrees Celsius. On the surface above, a chain of volcanic mountains erupts into being, and in the deep, a Trinic and Philippine plates. But when 2 continents collide, neither yields. The result is a monumental crumpling of the crust, folding and forcing rock skyward to form the highest mountain systems on the planet, the Alps, the Himalayas. The collision that raised the roof of the world began some 40 million years ago, when the Indo-Australian plate slammed into Eurasia. That journey is not over. India continues its push northward at a rate of 5 centimeters per year, and the Himalayas continue to grow. Elsewhere, the plates do not meet head-on, but slide past one another. The friction is immense, building tension along the shared edge until it is catastrophically released in the form of an earthquake. In California, the North American plate grinds along the Pacific, a seismic struggle that has etched the San Andreas Fault into the landscape. The arrival of this grand unifying theory irrevocably changed our view of the planet's evolution. It is a concept so fundamental it is rightly placed alongside Darwin's theory of evolution and Einstein's relativity. Yet it is not a static truth. As our knowledge deepens, the classical view evolves, revealing a system of staggering complexity. Plate tectonics appears less as a simple mechanical process and more as a planetary self-regulating mechanism, a living system where destruction enables creation, and the slow, inexorable forces of the deep earth continuously write and rewrite the story of the world above. The systems that compose our world are locked in an eternal dialogue. We have long understood that mountains command the climate, shaping the flow of wind and water. But now, a more profound and unsettling truth is emerging. The climate, in turn, shapes the very mountains. It reaches into the planet's depths, influencing the titanic forces of tectonics. Consider the Andes, a spine of rock born from the collision of 2 worlds, where the oceanic Nazca plate dives beneath the South American continent. In the humid south, relentless rain and ice scour the peaks. This erosion washes immense volumes of sediment into the Pacific, lubricating the fault line, easing the friction between the grinding plates. But to the north, the climate is arid, hostile. Here, almost no sediment forms. The oceanic plate is not lubricated. It scrapes and gouges the raw edge of the continent. The friction is so immense that the mountains are forced ever higher, creating a formidable wall that starves the land of the very rains that might have tamed it. A feedback loop, written in stone and sky, where a dry climate builds its own prison. This intricate dance between rock and rain forces us to reconsider the very engine driving the continents. For decades, the prevailing theory has pointed to slow convection currents in the mantle, a thermal ballet between the planet's molten core and its crust. Yet this explanation struggles to account for the complex movements we observe. The great geological revolution, sparked by Alfred Wegener's once heretical idea of drifting continents, is far from over. The ambiguity he faced echoes in our own time. We are still haunted by the same fundamental questions, now centered on the ghost of a lost world, the supercontinent of Pangaea. How did this colossal landmass assemble? And more mysteriously, why did it tear itself apart? The answers remain elusive, buried under hundreds of millions of years of geologic time. There is no single, agreed-upon version of events. Instead, competing theories vie for supremacy. Modern modeling reveals an even more staggering reality. The assembly of Pangaea was not a singular event. It was merely the latest chapter in a cyclical epic. Roughly every 800 million years after the previous supercontinent has shattered, the pieces begin their slow journey back toward one another, destined to repeat the drama of creation and dissolution. In the space of less than a century, a picture of this ancient world has been redrawn again and again. Wegener himself could only reconstruct Pangaea's northern half. Each new discovery, each deeper insight, only serves to highlight how much we have yet to learn. The ground beneath our feet is not a static stage, but a living, breathing entity, constantly remaking itself. The revolution continues, not in sudden upheavals, but in the slow, inexorable shift of our own understanding. Deep within the earth, an ancient engine stirs. Fueled by the slow, inexorable fire of radioactive decay, vast currents of molten rock churn in a planetary-scale convection. This is the unseen force that builds worlds and tears them asunder. Upon this boiling interior, tittered by the heat rising from below. For a time, they were one. Pangaea, a single, immense landmass whose sheer scale may have upset the very balance of the planet, subtly altering the rotation of the Earth itself. But such monolithic arrangements are not destined to last. 150 million years ago, the great continent began to fracture. Did it become a victim of its own colossal size, its own weight, breaking its back along ancient lines of weakness? The lithospheric cluster broke into two vast chunks. To the north, Laurasia, comprising the future territories of North America, Greenland, Europe, and Asia. To the south, Gondwana, a union of what would become South America, Africa, Antarctica, India, and Australia. But the sundering was not over. 120 million years ago, Gondwana also began to splinter. Between the separating jaws of Africa and South America, a new world was born. The Atlantic Ocean began its gradual expansion, new oceanic crust endlessly forming along the mid-Atlantic ridge. A vast volcanic seam stitched the planet together even as its land masses pulled apart. Africa drifted, leaving a fragment of itself behind, the island of Madagascar, as it journeyed toward Asia. This epic of creation and destruction has played out more than once. The Earth remembers other supercontinents, their histories written in stone. Rodinia, assembled 1 billion years in the past, met a similar fate, shattering 750 million years ago. These are the deep rhythms of our world, a cycle of continental aggregation and dispersal that operates on a time scale almost beyond human comprehension. The landscapes we call home, the coastlines we map, are merely a snapshot in a geological moment. The continents are not fixed anchors in time, but temporary rafts on a sea of fire. The same forces that broke Pangaea are still at work, silently pulling, pushing, and reshaping the world beneath our feet, a constant reminder that the face of the earth is never truly finished. It is merely waiting for its next form. The continent of Asia crumpled, buckling into gigantic folds of rock we call the Himalayas. From the silent vantage of space, the edge of the continental plate appears shattered, crushed by a force beyond imagining. One can almost feel the colossal pressure that thrust Everest towards the heavens, creating a mountain range with the deceptive ease of a wrinkle in a tablecloth. Elsewhere, a similar tectonic drama played out, as the slow collision of Africa and Europe gave birth to the Alps. But this grand narrative of colliding plates may not be the whole story. To explain the primordial breakup of the supercontinents, the very fragmentation of our world, scientists are far from consensus. Some are convinced that the principal role was not played by the stretching and cracking of the crust, but by a far deeper, more mysterious force. For evidence, geologists have long looked to a peculiar island ridge in the central Pacific Ocean. Here, the Hawaiian Islands form a chain of volcanoes stretching for nearly 3,500 kilometers, more than 2,000 miles. The youngest among them, Mauna Loa and Kilauea, still bleed molten rock. Yet the most distant and ancient volcano in this chain was active more than 40 million years ago. All of them were born from a single source, a so-called hotspot. It is a relentless outpouring of magma, a plume of superheated material rising from the deep mantle to burn a hole through the lithosphere above. Where it breaks through, a volcano is born. This hotspot is believed to be stationary, a fixed blowtorch in the planet's interior, while the oceanic plate drifts slowly over it. The result is a geological production line. A volcano forms, is carried away from its magmatic source by the moving plate, and dies. Beside it, a new one is born. It is as if a sheet of paper were being dragged across a lit candle, leaving a trail of scorched brown spots. Thus, a chain of volcanoes, a gradient of ages, marks the passage of the Pacific Plate over this deep terrestrial flame. Today, Liquid lava flows from Hawaiian volcanoes with a deceptive tranquility, spreading across the land without destructive explosions. It solidifies quietly, sometimes crumbling into angular blocks, sometimes sealing the earth beneath a smooth black crust. But they were not always so quiet. In hotter periods of Earth's history, the planet's volcanism was a cataclysm. Scientists have discovered layers of frozen lava a kilometer thick, flood basalts whose surface area exceeds the entire Scandinavian peninsula. Here, volcanoes must have raged without pause for millions of years. The cause is thought to be mantle jets of unprecedented strength, tearing through the lithosphere with ease. But what could give rise to such gargantuan plumes? The answer may lie in areas of anomalous heating deep within the Earth. Beneath the oceans, the crust is a fragile shell, sometimes only a dozen kilometers thick. Hot rock from below can easily heat this thin envelope and find its way to the surface. But beneath the continents, the crust is a formidable shield, reaching a thickness of 30 to 80 kilometers. For the planet's inner fire to break through that, the pressure, the heat, and the force must build to a scale that is truly, fundamentally world-shattering. Deep within the Earth's bowels, a colossal furnace rages. Above it, the continents drift, acting as immense shields, reliably protecting the surface from this infernal heat. But when a landmass swells to a critical size, it becomes a thermal prison. An abnormal amount of heat accumulates beneath it, until a superheated jet of mantle rock begins its slow, inexorable ascent. Trapped by the insulating lithosphere, it cannot break through. Instead, it spreads, a vast horizontal current of molten material, undermining the very foundations of the world above. This powerful flow scours the base of the continent, thinning it over millennia, until with a final violent shudder, it is torn asunder. Along the newly opened fissure, the planet bleeds. Glowing rock from the deep earth is unleashed, and prolonged volcanic eruptions begin, painting the sky with ash and the land with fire. If this hypothesis holds true, the scars of such a cataclysm should be etched into our modern world, and they are. Traces of these ancient eruptions are preserved along the Atlantic coasts of Africa, South America, and Europe, the very seams where the supercontinent Pangaea was ripped apart. Here, vast layers of basalt bear silent witness, rock that poured forth precisely when Pangaea was breaking into fragments. The same titanic forces are believed to have engineered the collapse of Gondwana, once the largest continent in the southern hemisphere, a single landmass comprising modern Africa, Australia, South America, Antarctica, India, and Madagascar. Beginning approximately 160 million years ago, both Gondwana and its northern counterpart, Laurasia, began to fracture. The spaces between them became the new oceans, the Atlantic, the Indian, the Arctic. Slowly, agonizingly, the map of the Earth began to acquire its familiar face. Pangaea itself, a world continent born in the Paleozoic era, had endured for nearly 290 million years. It was a period that saw the flourishing of complex life, only to end in mass extinction. As this supercontinent was slowly unstitched along the rift, the sea periodically invaded the deepening valleys. By the end of this process, the physical world was transformed. This new geographic arrangement of land and sea had profound consequences for the planet's climate and for the entire course of biological evolution. The circulation of the oceans, the planet's primary mechanism for transferring heat, was radically altered. Life on our planet was irrevocably changed. Newly formed ocean basins became impassable barriers, isolating populations of plants and animals, setting them on separate evolutionary paths. The surface of our world, which feels so permanent, is merely a fleeting arrangement in a geological drama that has played out for eons. The very shape of life is not dictated by biology alone, but is carved, directed, and forever defined by the slow, violent breathing of the planet itself. The shattering of a supercontinent was not merely a drama for the creatures of the land, it was a cataclysm that reshaped the very oceans themselves. The collapse of Pangaea was a pivotal moment in the formation of our world, an event so profound its consequences echo in the distribution of life and the climate we experience today. It began at the close of the Paleozoic era. A finger of the great global ocean pushed its way westward into the heart of the landmass, carving a channel into the region we now recognize as the Mediterranean. This relentless oceanic intrusion crept further, a slow motion tearing that split the future continents of Europe and Africa. A new sea was born from this wound in the Earth's crust, a vast east-to-west basin known to geologists as the Tethys Ocean. Its arrival was a climatic revolution. For the first time in ages, warm equatorial currents had a pathway through the supercontinent, fundamentally altering the planet's weather engine. The Great Rifting continued its inexorable march west, a geological fissure that would eventually sever South America from its northern counterpart. In the infancy of these new continents, seawater would periodically flood the basins, only to bake away under an unforgiving sun, leaving behind vast deposits of salt. These Triassic evaporates, the mineral ghosts of vanished seas, can still be found today, tracing the northwestern edge of Africa and scattered across Europe. But to understand this era is to understand a world of extremes. Evidence, written in the language of stone and bone, tells of a climate of punishing dryness, especially in the vast interior of Pangaea. The fossilized remains of flora and fauna, alongside the testimony of sedimentary rock, paint a picture of a great desert at the heart of the world. Researchers believe the central continent was intensely arid, starved of moisture. This was a world locked in a rain shadow, surrounded by towering mountain ranges that blocked the passage of life-giving clouds. The landscape itself speaks of this lost, dry world. An abundance of ancient sandstone and petrified dunes are a telling feature. Today, such dunes are the signature of hot, arid deserts, and there is no reason to believe the past was any different. While sandstone can form in many environments, the story of its origin is locked within its structure. The wind, a selective carrier, can only transport the finest grains, leaving larger pebbles behind. The resulting dunes are therefore composed of small, uniformly sorted particles, a stark contrast to the chaotic mix of sands deposited by rivers or along coastlines. The very layers of the rock, a frozen record of sedimentation, tell a story of wind, not water. Yet, these silent dunes are not the only witnesses. The Permian period is distinguished by thick strata of evaporates. These are beds of pure salt, formed where arms of the sea became isolated from the open ocean. Trapped, these basins slowly dried out over millennia, their water vanishing into the thin, dry air, leaving behind only the dissolved minerals they once held. These layers of salt and seas of sand are more than geological curiosities. They are pages from the Earth's deep history, a chronicle of a world being torn apart and remade by forces of unimaginable scale. They remind us that the ground beneath our feet is not static, but a dynamic canvas, forever shaped by the memory of lost oceans and forgotten deserts. In the silent language of stone, the earth tells a story of a lost world. Vast fields of ancient salt and petrified sand dunes whisper of a climate long past, a planet that was overwhelmingly warm and dry. Yet this simple portrait of an arid supercontinent is a mirage. Geologists remain divided, wrestling with a profound question. Pangaea was a world bisected by the equator, and many of these telltale deposits lie in what were once the low latitudes. Was the entire planet truly a furnace, or is this evidence merely a quirk of geography? The sheer scale of this single landmass created its own brutal climate, a vast interior of punishing extremes, with scorching summers giving way to frigid winters. But buried elsewhere, another clue emerges, contradicting the narrative of a desolate world. Seams of ancient coal, the compressed remains of life, reveal that parts of Pangaea nearest the equator were choked with lush tropical rainforests. To reconstruct with precision the climate of a planet 250 million years in the past is an act of careful speculation. The data is a whisper from an immense distance, but one fact is undeniable, a key that unlocks the mystery of life in this era. The continents were one. And because they were not yet sundered by oceans, life could walk across the globe. This is the only reason the fossil remains of Synognathus, a formidable Triassic reptile, can be unearthed in both the soils of South America and the bedrock of Africa. They were neighbors in a world without divides. 300 million years ago, as the Paleozoic era drew to a close, primitive mammals already navigated lands covered in abundant forests. It was here that reptiles began their ascent, multiplying rapidly in a world ripe for conquest. The fauna of Pangaea was a menagerie of the strange and the prophetic. Herds of Lystrosaurus and the plant-eating Traversodontidae, creatures considered distant ancestors to all mammals, were numerous across the landscape. During the Triassic period, the first archosaurs appeared, a dynasty that would eventually give rise to modern crocodiles and birds. And from their ranks, a new kind of creature was stirring. At the close of the Triassic, the dinosaurs finally arrived, but these were not the titans of later ages. Researchers believe these pioneers were different. built with porous bones and perhaps cloaked not in scales, but in a coat of primitive feathers. For tens of millions of years, the slow, inexorable dance of the continents continued. The influence of this immense landmass would shape the planet's climate deep into the Mesozoic era. The world we know was born from its fragmentation, and the creatures that walk it are the distant heirs of those that roamed a single, unified earth. We are left with fragments, a bone here, a seam of coal there, each a fleeting glimpse into a planet so alien it is almost beyond imagination. In the deep past, the world was a silent, alien kingdom. Life was not yet etched in familiar forms. The land was largely barren, a vast, waiting stage. The great drama of existence unfolded almost entirely in the sea. Here, in the planet's sprawling oceans, organisms flooded every possible habitat. They built the first empires in the shallow waters and freshwater skeletons, while ancient sponges, the archaeocathids, filtered the primordial currents. Microscopic bryozoans formed colonies of staggering complexity and variety. This was the crucible of evolution, a period that saw an explosion of new classes and types of living beings. Trilobites, marine arthropods exclusive to this Paleozoic era, were masters of this domain. Amphibians, the tentative pioneers of the land, remained few in number, their lives still tethered to the water's edge. Upon the supercontinent of Pangaea, a revolution was taking root. Plants, once simple and low-lying, were becoming architects of a new world. Their fertilization was no longer shackled to the presence of liquid water. A new strategy emerged: dissemination. Pollen, a microscopic vessel of life, could now travel for thousands of kilometers, carried on the wind to find its counterpart. Seeds were transported by air, by water, and by the first animals to walk the earth, allowing species to conquer barren territories and forge new ecosystems. The microscopic testimony of ancient spores tells of a world in flux. The great gymnosperms, the naked seed plants now represented by conifers, were decimated. In the northern hemisphere, they were replaced by lecopsids. The extinct genus Pleuromaea was a dominant force, its leafless stems reaching 2 to 3 meters into the sky, with fossil specimens unearthed in Russia, Europe, China, and Australia. In the southern hemisphere of Pangaea, the landscape belonged to a different sovereign. Here, the Permian flora was composed almost entirely of Glossopteris, an extinct seed fern that could grow into towering trees, its leaves measuring anywhere from 2 to 30 centimeters long. But after the catastrophic mass extinction of the Permian-Triassic crisis, this flora vanished, replaced by a similar type known as Dicroidium. The aftermath of this great dying is written in stone as a profound absence. There is a dearth of fossilized plants, a near-total lack of charcoal, suggesting a world without fire because there was so little to burn. Instead, the record shows a sudden, dramatic spike in organic walled microfossils. These have been interpreted as the spectral remains of fungi, the great decomposers. The continents, it seems, were not covered in forests, but in a vast, silent blanket of decaying life. And yet, from that distant epoch of giants and ghosts, a single living witness remains. The ginkgo biloba is the last surviving species of its order, a lineage that began some 280 million years ago, when the world was one. It saw the rise of the great Paleozoic forests and endured their fall. It is a living relic from a time before flowers, a quiet testament that even as entire worlds perish, life is a thread that can endure through the unfathomable depths of time. It can stand 40 meters tall, a silent witness for over 1,000 years. The ginkgo biloba, a living fossil whose ancestors saw the end of a world. 252 million years ago, the Earth was a different planet, inhabited by bizarre life forms, the prototypes of dinosaurs and reptiles of enormous scale. But at the close of the Permian period, this vibrant world faced the largest extinction event in its history. It is a cataclysm known as the Great Dying. The statistics are almost unfathomable. According to the latest estimates, between 93 and 97% of all life in the seas vanished. On land, nearly 2/3 of all animals and plants disappeared forever. For paleontologists, the sheer totality of this event remains one of history's greatest mysteries. The prime suspect is a planetary catastrophe that began 250 million years ago, a slow-burning apocalypse that virtually erased the ancient forests. Evidence points to a world in its death throes. A sharp decrease in oxygen saturation poisoned the global ocean, while the atmosphere filled with the suffocating blanket of carbon dioxide and methane. Intense acid rain lashed the continents, altering the very chemistry of the seas and dissolving the world's coral reefs into oblivion. As global warming intensified, the Earth was gradually, inexorably, transformed into a lifeless desert. For millennia, the cataclysm dragged on, the climate pendulum swinging from one extreme to the other. Devastating periods of heat were replaced by sudden, brutal cold. But the ultimate source of all this destruction lay deeper. The trigger was set 50 million years before the dying began. A hypothesis points to the large-scale movement of tectonic plates, the slow, colossal dance that was forging the supercontinent of Pangaea. As continents collided, vast sections of crust sank into the mantle, thickening the Earth's skin and deepening the world's oceans. Around 300 million years ago, these profound geological processes may have caused the planet's magnetic poles to reverse. More critically, an immense amount of cold material plunged into the Earth's molten interior, forming a volatile plume. It was a geological time bomb. Yet, from the crucible of this global extinction, life endured. Among the few survivors were creatures that would become the ancestors of modern birds. And in the ashes of the old world, the first species of dinosaurs took their first steps. The ginkgo tree, which survived the devastation, still stands. It is a living testament not just to the planet's capacity for destruction, but to the relentless, unyielding persistence of life itself. Deep within the Earth, A slow, inexorable current stirs. For millions of years, thermal convection has driven plumes of superheated rock towards the planet's fragile crust. 251 million years ago, on the territory of modern Siberia, this interior pressure finally broke through. Lava bled across the surface, covering more than 4 million square kilometers, an area vast enough to swallow modern France 7 times over. It was a wound on a planetary scale. Nearly 10 million years earlier, a similar fissure had torn open the crust in what is now southern China. Some Chinese scientists point to these two colossal eruptions, born from the massive convergence of tectonic plates, as the genesis of a global catastrophe. They argue this was the source of a primordial poison, a tide of greenhouse gases and acid rain that choked the world long before the first dinosaurs walked the earth. Yet, in the quiet halls of geology, this theory remains a point of fierce contention. The most glaring issue is a chasm in time. A 50-million-year gap separates the formation of the supercontinent Pangaea from these volcanic outpourings. For many researchers, the cause of the great dying must be sought in events chronologically closer to the extinction itself. But the ultimate legacy of Pangaea's birth and eventual demise is undisputed. It was a mass extinction, a cleansing fire that reset the course of life. In its wake, new species of plants and animals would rise to populate the next era. What if that world had never ended? What if Pangaea had not broken apart? To compare our modern Earth with its image from the age of the dinosaurs is to see two different worlds. Were the continents still one, our own countries would be unrecognizable. Many would occupy entirely different latitudes, their climates transformed. Siberia could be a subtropical paradise, a mirror of modern California. It would not only be the maps and the weather that would change, but the very fabric of life itself. On a single, unified landmass, fauna would have followed a profoundly different evolutionary path. The Earth would be inhabited by creatures unknown to us, a menagerie of life whose diversity we can only begin to imagine. For humanity, such a world would present a radically altered reality. A single continent implies an unparalleled ease of movement. Land transport would be the undisputed king, with every corner of globe reachable without crossing an ocean. Air travel would be faster, more direct. But this profound connectivity would carry a darker implication. Without the natural buffer of oceans, the political landscape would be infinitely more volatile. The conditions for war would be simplified, troop movements terrifyingly swift. Any conflict could become a global one with breathtaking speed. This entire thought experiment, however, rests on a fragile assumption that our species could have ever been born in such a world, that the unique evolutionary pressures of our fragmented continents were not the very crucible in which humanity was forged. The continents are not static. They are adrift on a sea of magma, locked in a slow cosmic dance. According to the geological rhythm known as the Wilson cycle, supercontinents are a recurring feature of our planet, forming, shattering and reforming every 400 to 500 million years. The world we know is merely a fleeting arrangement, a temporary snapshot, in the deep time of a planet that is constantly remaking itself. The great continent is not just a ghost of the past, but a promise of the inevitable future. The continents are embarked on an imperceptible journey, a slow-motion collision course so vast in its timescale that no human will ever witness its conclusion. We are but fleeting passengers on a planet in constant silent transformation, left only to guess at the consequences of this eventual colossal unification. To glimpse this distant future, we must first look back into the deep past. For the more precisely scientists can restore the face of ancient Earth, the clearer their visions of its future become. The world we know is merely a temporary arrangement. Before Pangaea, other supercontinents reigned. Its own assembly was but a brief episode in a far grander saga, a momentary union in an eternity of fragmentation, where scattered land masses drifted across immense, now vanished oceans. Tectonic evolution acts as the planet's master tailor, stitching togeways the same, the ancient cratons and continental cores. But with each new cycle, the cut is different. Oceans that once separated these lands are slowly crushed out of existence as the continents converge, until a single, world-spanning landmass is born. This is the Great Terrestrial Rhythm, a cycle of continental unification and dispersal that repeats roughly every 500 million years. We are now halfway through the current cycle. In a future as distant to us as the first dinosaurs are in the past, some 250 million years from now, the Earth will be remade. A hypothetical new world, Pangaea Ultima, will emerge, a colossal continent forged from the amalgamation of Africa, Australia, Eurasia, the Americas, and Antarctica. Perhaps all the lands we know today will converge within the basin of the dying Pacific Ocean, forming a single supercontinent, only to later fracture under its own immense weight, its fragments beginning their slow drift in the opposite direction, initiating the next great cycle. The first tremors of this future world are already detectable. The Red Sea Rift is a nascent ocean, tearing a continent apart. Africa grinds inexorably towards Eurasia at a rate of 3 to 4 centimeters per year, squeezing the Mediterranean Sea into oblivion. As the Atlantic Ocean widens, the Pacific shrinks. To the east, the Indian Plate continues its relentless northward push, crumpling the Eurasian Plate and thrusting the Tibetan Plateau ever higher into the sky. These movements, measured by paleomagnetic data locked in ancient stone, are the subtle but undeniable proof of the planet's restlessness. They remind us that the maps we draw are not permanent records, but mere snapshots of a single moment in an immense geological epic. The Earth is not a static stage for our history, but a living, breathing entity, forever erasing the worlds that came before and building the ones that are yet to be. The silent, imperceptible breathing of the planet is now measured. Through a network of satellites, a science known as geodesy, tracks the slow, inexorable drift of the ground beneath our feet. What were once theories are now physical certainties, long-term observations of a world in constant grinding motion. The models born from this data do not speak of centuries, but of epochs. 30 million years from now, the Japanese island arc will complete its journey, welding itself to the coast of the Russian Far East. Within the vastness of the Eurasian continent, the crust may first stretch and break, opening a new internal sea, only to later tear apart completely, forging a nascent ocean between the separating Siberian and Amur plates. 250 million years into this future, the globe is unrecognizable. The North American continent will have pivoted counterclockwise, pushing Alaska into the warmth of the subtropical belt. Eurasia, in a complementary motion, will continue its clockwise turn. The British Isles will find themselves locked in ice at the North Pole, while Siberia thaws in a temperate sun. The Mediterranean, cradle of civilizations, will be crushed out of existence, its floor forced skyward to form a mountain range rivaling the Himalayas. This is the assembly of the next supercontinent, Pangaea Ultima. It will be a harsh world, a vast singular landmass covered by 90% desert. Giant mountain ranges will scar its northwestern and southeastern flanks, the titanic wrinkles from a planetary collision. Our world will, in a sense, have come full circle, resembling the planet as it was some 335 million years ago. This is not a singular event, but a rhythm. Throughout Earth's deep history, continents have danced, converging, shattering, and converging again. The tremors we feel as earthquakes are merely the shudder and percussion of this deep engine, the violent evidence of plates shifting against one another. Even now, Australia drifts steadily towards Asia, a continental envoy signaling the first steps toward the next great gathering. The time scale for such a transformation is almost beyond human comprehension. It can take 300 to 400 million years for a supercontinent to form, and just as long for it to be ripped apart by the heat churning below. The globe we recognize, the familiar contours of coastlines and oceans, is a fleeting snapshot, a temporary arrangement. Today, scientists calculate that 85% of our planet is habitable. But this is a fragile, momentary grace. The maps we draw are not permanent records, but a single frame in an impossibly long film, a testament to the fact that the only constant on Earth is change itself. Beyond the horizon of our own time, the relentless dance of the continents continues. Scientists now look forward, projecting the forces of geology to glimpse the face of a world to come, a new supercontinent, born from the slow collision of our own. Should the land masses converge into the predicted Pangaea Ultima, they will lock together in a vast belt, girdling the planet's equator. The Earth as we know it will cease to exist. In this future, the great polar ice sheets, titans of our current age, will have vanished. Ice will become a relic, clinging only to the rarefied air of the highest mountain summits. With its reflective white shields gone, the planet will absorb the sun's energy, with an unforgiving intensity. The world will warm, returning to a hothouse climate not seen since the Mesozoic, the age of dinosaurs. The global average temperature is projected to settle near 20 degrees Celsius, some 68 degrees Fahrenheit. Under these conditions, vast swathes of this new world, nearly 99.8% of its land, will become habitable. Clustered in the life-giving warmth of the equatorial and tropical zones, the stage will be set for an explosion of biodiversity, a new genesis on an almost forgotten scale. The precise cartography of this future world remains shrouded in the depths of geologic time. Our grasp of plate tectonics does not yet permit such a perfect prophecy. But of the outcome, there is little doubt. The continents are on an inevitable course, destined to merge millions of years from now. The Earth does not remember our maps or our borders, only the slow, inexorable rhythm of its own creation.